and listen to my story about a man named Jed. A poor mountaineer barely kept his family fed. And then one day he was shooting at some food, and up through the ground come a bubbling.
One thing that intro makes apparent is that the industry has come a long way since I was a little kid. When we talk about fossil fuel resources, oil and gas, the first thing we should discuss is where it comes from. It's formed in source beds. These are characteristic special environments that accumulate organic matter. Subsequently, once the oil forms or the gas forms in these source beds, it may migrate, and it'll migrate depending on the porosity and permeability, the ability for materials to move through rock. It may make this migration to a reservoir where it can ultimately be recovered as either crude oil, which is the raw form of petroleum, the native form as it comes out of the ground, or as natural gas, which is dominated by the gas methane. Now, when we talk about conditions of formations in the oil industry, it's called an oil window. This is a bit like making sourdough bread. If you follow the instructions, use the right ingredients, obey the rules, you will get something that looks like this. If you don't obey the rules, you'll get some kind of inedible blob. Okay, same with oil. If the source materials are placed in the proper environment and given the amount of time that they need, they will develop into something good. If we're lucky, this crude oil is going to reside in a porous rock that we're going to call a reservoir. And it's also known as an oil trap. The oil is accumulated and contained by that reservoir, by that trap. Gas is going to do the same kind of thing. It's a little more mobile than oil, but it's going to be subject to the same conditions of formation, largely, and the same conditions for migration and preservation. So here we can take a look at a diagram of a couple different primary types of oil reservoirs. What we're going to see in these diagrams are the oil pumps, the location of the oil, location of gas, and its relationship to surrounding rock. In this case, as I mentioned a little bit earlier in lecture, we have an anticlinal trap. So an anticline forms in sedimentary sequence through compressional tectonics, most likely. And this anticline is going to form some space that oil and gas can migrate to. Oil and gas are going to migrate through this fluid, in this case mostly water, because they're lighter, they're less dense than the surrounding water. So they're going to move upward until they're trapped above this solution. In the case of a fault trap, we have the displacement of rock, in this case a water-saturated source rock that's also going to be our reservoir. We're going to truncate it. We're going to seal it off on one end, and any material in this bed that's capable of movement is going to move, in this case the oil and gas, to the highest point in that reservoir. And it's going to be trapped by an impermeable shale, just like in this anticlinal trap here. In the case of a stratigraphic trap, we have the original deposition, the original splays of shale adjacent to splays of sand and silt. They're going to form a trap with barriers of impermeable shale on the boundaries. So this is going to be, in this case, a pretty cheap reservoir to get into. It's near the surface. Gas is going to be very easy to get. Oil, not too much more difficult. And in the case of the salt dome trap, these are big in the Gulf of Mexico and actually in a lot of other environments. So here we have a diapir, a blob of salt that's going to rise plastically, like the blobs of paraffin in a lava lamp. So they're going to rise like stomping on a jelly donut. The weight of the surrounding material is going to force that diapir upwards. Squeeze down on it and force it upward. As it's forced upward, it's going to bend these sedimentary rocks around itself and, in a way, form an anticline. So in this case, it's going to also form a barrier against migration of the oil and the gas. This is very tight, impermeable material adjacent to other impermeable tight material, the shale here. So combined shale and salt provide a great trap for oil. So these are the kind of structures that are drilled into in Texas and Louisiana, down around the Gulf Coast of the U.S. Now, fracking has come along recently as a big deal. It's a big deal in terms of generating lots of oil and gas cheaply, and it's a big deal in terms of polluting the groundwater and causing earthquakes and a variety of other environmental disasters. So in this instance, oil and gas can be found in tight formations. These tight formations are called tight formations because they're sealed with impermeable source bedrock. And as a result, the extraction is going to be difficult. You can't get the oil and gas to move through this material unless you do something to that material. And what's done is horizontal drilling and hydraulic fracturing. So this is an image from Texas. These are fracking pads. You can see they're very densely spaced, and that means they're targeting little bits of oil and gas deposits in generally tight formations. So the way this works is we drill a hole and you add a series of shunts. By putting these shunts down in the borehole, you can change the direction of the drill. So in this case, the shunts direct the drill bit at a 90-degree angle relative to the initial barrel, and it's going to be encased in cement. Then small holes are going to be blasted through that cement, which also fractures the surrounding tight bedrock. To keep this from coming back together again, collapsing on itself, water and particles are pumped into these fractures, and these act as little spacers to keep these fractures open. Also pumped into this, and it's one of the more controversial aspects of fracking, is some kind of proprietary solvent. And this proprietary solvent is good at keeping liquid oil and gas moving through these fractures. It's also often very toxic, and it ends up in the drinking water of houses that are near these fracking sites. So fracking is going to generate small fissures, small cracks that are going to be kept open by jamming sand grains in there. So jamming these sand grains prevents the collapse. The proprietary toxic solvent keeps the oil and gas from clogging up these conduits, and lots of money is to be made for a fairly short amount of time. When we look at global distribution of oil resources, here we see that a number of countries are particularly rich in oil, Saudi Arabia and Venezuela being the two richest in the total amount of proven reserves. Coming up next, countries like Canada, Iraq, and Iran, and then less well-endowed countries like Russia, Algeria, Libya, and Brazil, the US, and then the have-nots in the light yellow and gray. The dominant sources of oil are going to continue to be the Middle East for a while, and Russia. The Middle East and Russia are the regions that are currently keeping oil prices down, which is directly affecting the economy of Canada and more severely affecting the economy of Venezuela. The U.S. Gulf Coast and Caribbean are going to continue to be active, but not as active as they had been in the past. And then we have other areas that pop up on occasion as brief, moderate sources of oil. Looking at reserves over a period of time, you'll notice that reserves have gone up instead of down. And this is because of new technologies like fracking. As we use fracking to access tight formations, we have access to more oil. That's pretty much everywhere. So it looks like one could argue that we're producing more and more oil all the time. The price should go down, and this is a great thing. That life is going to get better as oil gets cheaper, but there's a limit to this. The oil consumption and production of countries around the world as of 2018 was 30 billion barrels a year, with the U.S. producing about 4 billion barrels a year. Top producers in 2020 are the United States at 19.5 billion barrels per day, Saudi Arabia, a little more than half of that at almost 12 million barrels per day, Russia, also around 11 to 12 million barrels per day. Canada, about half of that at 5.5 million barrels per day. And China, Iraq, UAE, and Brazil round out this top 10 here. So this brings up an interesting idea. This is an idea that was put forward in 1938 by someone named Hubbert. Hubbert's peak shows the time of maximum production. This is going to differ from country to country, as oil fields are discovered and become depleted when we've used up half of a given reserve. So that's the halfway point for consumption of a given country's oil. Originally, Texas hit its peak in 1971. The rest of the U.S. also 1971. Alaska, the big North Slope project, boosted that to 1989. And you'll see a number of other countries here. Canada, its conventional resources peaked in 1974. Then modern reservoirs are completely different. So Canada's back in the game again. But nonetheless, all these countries are going to peak and then run out of oil. The reason this peak is moving, and in the US it started in 2008, is that new technologies come online. So the original date of peak production was 1971. We've passed that, obviously, and productivity is again on the rise. And it's on the rise because we're using fracking, something that wasn't available back in the 60s, 70s, certainly not in the 30s when the idea first came about for this peaking of oil production. What is fracking doing to the oil and gas industry, and in particular in the US? And what it's doing is changing the price of gas. The amount of gas available, conventional gas, has decreased. So we've peaked and we're running low. Gas from tight formations is on the rise, and it will continue to rise until it becomes too expensive to get, and we're right about that mark right now, which is why we're seeing the shutdown of oil and gas fields all over the northern US and in Canada. Which brings us to coal. We have enough coal to last hundreds of years. Hopefully we won't have to use it. Lignite is about 70% carbon, so it's the light brown, cheap, easy to get at coal, very common. Subbituminous, higher energy content, less common. Bituminous, even higher energy content, even less common. And then we have the king of coal, anthracite, 90% carbon. It's had all the juices baked out of it, so we don't have to burn the volatiles. You don't expend energy on that. It's pure, hard, dark, shiny black stuff. 90% carbon. Where do we find this stuff? We find lignite in enormous deposits in the Dakotas. This is North Dakota, South Dakota, Montana. That's where most of it is. Subbituminous coal, again, huge deposits in Montana and Wyoming. Wyoming here. The big Montana deposits up here. And then a smattering throughout Colorado and New Mexico, a little bit in Arizona. Bituminous coal. That's much of the Midwestern coal and the Appalachian coals here, the Western Appalachian coals. And then anthracite, the good stuff, is located here in the Appalachians, where it has been baked by our collisions with Europe and Africa. The bad stuff in oil include the tar sands, heavy oils from the tar sands. These are expensive to get, they're energy intensive to get at, and they're located in a place that isn't near any particular energy interest. There's no big industry going on in northern Alberta. Known as bitumen in the UK, or bitumen in the United States, is contained in oil shales. These oil shales look and feel just like regular shales, except they've got a significant amount of oil locked up in them. And it's locked up pretty tightly, so the shale has to be processed. And this is an expensive process. It's a highly energy-consuming process, and it's quite rich in pollution. So not much better, if better at all, than the tar sands of Alberta. What we see here is typical extraction pit. The basically oily, thick sands, kind of asphalty, is scooped up and processed, again, using an enormous amount of energy. So the use of that energy itself is a pollutant. The production and processing of this heavy, dark, viscous oil that contains a lot of dangerous heavy metals and carcinogenic compounds is a significant source of pollution in of itself. And it's not only pollution working its way through the ground, through the groundwater, it's pollution that's traveling through the air. A very significant amount of heavy metals travels through the air. It's deposited on snowpack. When that snow melts, it goes into rivers and into Lake Athabasca. And we've seen a building case for environmental damage from carcinogenic compounds and the heavy metals as a result. Also, coming from these oil fields are enormous amounts of sulfur. These are sulfur blocks, native sulfur, elemental sulfur, that have no home. No one wants to buy this stuff. So it's just literally stacked up in enormous piles, mountains of sulfur as they're called, that are sitting out in the elements. When it rains or snows, you're adding water to sulfur and you get sulfuric acid. So these are giant acid generators. The burning of the oil itself generates acid rain via CO2 that forms carbonic acid when it enters the atmosphere, and sulfuric acid that's generated when this sulfur is mobilized. In addition to that, there's a contribution of carbon dioxide to the atmosphere, the greenhouse effect of burning coal and oil. This is an example of the removal of a mountaintop in the Appalachians. This takes place pretty commonly in West Virginia, eastern Kentucky, that region of the United States. It's easier just to remove the top of the mountain to get at the coal, and you're left with a mountain with the top chopped off. Now, we used to take advantage of this when I was a kid, or when I was an undergrad anyway, and we'd go riding in the strip mines on Sundays because the workers weren't there, and realistically, they didn't care much for the environment, so you could tear up the mine piles with your motorcycles. Now, oil in the environment has a different yet similar set of problems. Oil can easily spill during production, as we saw with the Deepwater Horizon disaster of about 10 years ago. Oil can spill during transportation, carried by pipelines or trucks or trains. It's often dumped from those carriers, and it forms carbon dioxide when it's consumed, which enters the atmosphere and again functions as a greenhouse gas to warm the atmosphere. So here we have a couple examples. This is a photo of the Deepwater Horizon disaster in the Gulf and the Keystone Pipeline leak in North Dakota, both of which are still in the news pretty regularly today. Just recently, the new administration in the United States canceled the pipeline, which runs through the Ogallala Aquifer, as we saw in the previous lecture, and that hopefully will prevent things like this from happening. The oil spill during the Deepwater Horizon disaster of 2010 was much more extensive, much more widespread, and you can see it in this image. Not a particularly clear image, but it's an image of the oil spill, and the typical result is the death of a large number of birds. These pelicans may or may not have been saved. I don't know. Further north, the Arctic National Wildlife Refuge contains a very large amount of oil and gas. It's ripe for the picking if you're willing to endanger the environment. Natural gas is widely claimed to burn more cleanly than coal. That's true. Natural gas has a higher carbon intensity than coal. Methane, which is a greenhouse gas, a very, very strong greenhouse gas, or very, very effective greenhouse gas, is converted into CO2, which is also an effective greenhouse gas when methane is burned. One of the issues with oil production these days is there's gas production almost always associated with that oil production. There's no way to get rid of the gas. It's too expensive to transport and store. Nobody wants to pay for it, so it's just wasted. And instead of just letting it blow off into the atmosphere as methane, it's generally flared off. And North Dakota, as an example, flares about 100 million cubic feet per day. That's enough to power about 500,000 houses per day, whatever that would mean in people, 2 million people or so. It's about a third of all the gas that's produced. So roughly 1/3, 33% of all gas that's produced is simply burned off, pumped away because it's useless to the companies.